Hello everyone, December 11th. Alright, we're gonna climb stairs first and then we're gonna go back to this and see how we can, I have an idea yesterday, but I haven't completely fulfilled this idea, so I'm gonna have to try it out. Right, we're gonna have to try it out. Alright, let's do this one first. Climb stairs. Takes n steps to reach the top. Each time you can either climb one or two steps. How many distinct ways can you climb to the top? So we have n steps, and you can do either one or you can do two, right? So if we want to know how many distinct ways to climb to the top, so to climb to the top, we want to know this, then we just know this, or we know this. So every one will be the sum of the previous two. Remember for this, yeah. So is that Fibonacci, right? That's Fibonacci number. So everything. So we're start from the first, n steps, and then this will have one way, right? And then this will have 0. So this is 1, and this will be this can be either, this will be 1 plus 1 will be 2, right? And then the next one will be 1 plus 2 will be 3. The next one will be 5. So what I think, this is like this is the basic DP, right? That's the very basic DP idea. N is equal to 1. Well, if n is smaller than 3, I'll return n. Otherwise, for rest equals pre and p and p, pp and p should be 1 and 2, right? Then for this in range 3 to probably n plus 1, what I'm gonna do is p current shall equal to p plus pp, right? And then pp and p equals p and current. Now I'm gonna return p, something like this, and test it. Is that right? Okay, looks to be right. Okay, so okay, you're right. This is just a very basic DP solution. First time was a long time ago. One can say pp equals p and pp. Ah, that is better. Yeah, I don't have to. We'll just say p plus pp. $70. All right. So again, the idea is at each one we need to find out what are the where, right? Where we can make the palindrome. And then we'll go to the previous one. All right, that would tell us how many we can form based on that, right? So like the previous, how many we can form with at least k. Okay, then we have this value. And then we'll go to the next one, we say how many we can form. So we add up, so at this one, we say how many we can form, right? Ending in this, how many we can form overall. And then, as we go up, if it cannot form, I can just keep this value. We just carry this value up. So in the future, if somebody reference here, we'll get a value. And that's sort of, so yeah, hold on. This, I think this might work. Oh shoot. Let's give it a shot. All right, so at each position is going to be, now let's have a DP. What is it gonna be? I actually have no idea. But the first one, okay? The first one is, everybody is gonna be a 0, right? And 0. Okay, this is what I think. So we say DPI equals this all previous indices such that, yeah, we have to make this define what this DP is, right? Such that S DP I 0 all the way to I is a palindrome, right? And then the next value is total number of hold on, we don't need total, it's the max number of substrings. Max number of substring in an optimal selection. Oh, well, it's not a total. Ha. Max substrings, right? Max substring that satisfy the requirement ending in SI. Okay, so oh, this first one might not be 0 actually. We say if it should be int k, if k is equal to 1, right? K equal to 1. Because k is 1 or larger. So if k is larger, then it's not. So if k is 1, then yeah. Right? 1 to ns. So every single one, we, okay, dp.append, right? We always append a dis. Let's do this, will be easier to handle. So we'll append this, and then first is gonna be I, because we can always make it self. Second one will be int k equal to 1. So everything will start with this, right? And then we need to check if this is good, then we have another one, right? We add to another one, then this is just plus equal 1. We say if si is equal to si minus 1, right? If they are two are the same, then dp is minus 1, 0 dot append I minus 1, and dp minus 1, 1 plus equal 1. Plus equal to int k is smaller or equal to 2, right? K is smaller or equal to 2. Yeah, so these are like hard we can do. And then we're going to go through just the previous one, right? We go through every one of them, and then we try to see if it fits, right? And then we have, yeah, so we say for j in dp should be I minus 1, 0, right? That's all of those. And then we need to do j minus 1, right? I'm going to say if j minus 1 is larger or equal to 0 and sj minus 1 is equal to si. So if these two are the same, so that is a new thing, right? I mean, that's a new from j minus 1. From j minus 1 to I, that's a new thing. So we need to see if it's and I minus j minus 1 plus 1, that's the total number, right? In this thing, if this is larger or equal to k, which this one can just be I minus j plus 1 plus 2, right? Be plus 2. Then we can say dp minus 1, 0 dot append. Oh, we should always do this. Hold on. If this, we need to always append j minus 1. And then we say, if this, then dp the maximum number. So now we need to say, okay, so we have this, right? And we have all of those possibilities, right? Or we can take this and we have all this possibility. We can take that, we can have all this possibility. And at each partition, we need to find a maximum value, right? We need to find the maximum value. We need to find the maximum value. How do we grow it up, though? Yeah, this is just say we have a lot of different options for partition, right? We have different options per partition. And we want a maximum partition. A number, so minimum partition. Oh, I need a plus 1. I need to add myself, right? Add myself. But this is the start. Like we should say, okay, this, right? And if this is true, then if k is smaller or equal to 2, well, if k is 2, then this will be 1, right? So I shall be fine. Now if k is 1, this is going to be 2. And then we say we go for this. Go for this. You know what? Nah, we shouldn't. I don't think we should do anything here. This should still be 0, right? And then we don't do anything there. We just we do append, okay? We do append that, but then that's not j minus 1, okay? So it have to be at least k, right? So it has to be some index. Well, honestly, it's the previous j, right? And then j minus 1. And then, yeah, this is right. This is right. J minus 1 is the previous one that we can try to see if we form a palindrome. And if we do, we add this, right? And then we'll see if it's larger or equal to k. If it is larger or equal to k, then we say dp minus 1, right? 1 shall equal to maximum dp minus 1, 1. And what is this and? Because I have 1 plus dp. I want to say j minus 1. Okay, I want to say j minus, because we're comparing to j minus 1. Because j minus 1 is forming a, holy crap, j minus 1. So hold on, what's this j? J is the previous one, and I can form a palindrome, and then j minus 1 is this, right? So we are looking at this thing. We're looking at this thing. Okay? We're looking at this thing. And then when we're looking at this thing, we want to know the maximum ending at the previous one. Right? With the maximum ending at the previous one. Ooh. Man, the maximum ending at this, the maximum ending at this, right? The maximum ending at this. Okay. dpj minus 1. No, that should be j minus 2, right? It shall be j minus 2, because j minus 1 is the one that's comparing to myself. So it has to be j minus 2. And then this has to be also, you know, j minus 2 is larger or equal to 0, right? If else is going to be 0. Alright, so we go through every single one of them. Then we'll have whatever the current value will be, which is the maximum ending at this. Right, the maximum ending at this. But once we handle everything, so if we handled everything, what we have is at this position the maximum, right? Then we're going to compare to the previous one, and we take the max because we want the max. It doesn't matter, we don't have to really, because it's just as long as it's non-overlapping, right? Then we say dp minus 1, 1 shall equal to the maximum dp minus 1, 1, and dp minus 2, 1. Okay, and then blah blah blah, we're gonna return dp minus 1, 1. Alright. I have no clue. This is going to be a trial and error. I can foresee it already. 0. Okay, we'll have is s and k. right? These two are correct. We need to get some. What the hell, man, you doing? Too much. Let's do 7. 3, 5, 6, 7. And then we say, okay, at least 2. In fact, we can do 2, 3, 4, 5, 6, 7. And then we do a 2, but I'll put a B in here somewhere. See if it works. A is not a. Wait, what? Oh, lordy. Sorry, I forgot. Has to be double quote. Nope. Not even close. It's okay. That is totally okay. Yeah, that's why we have this. Handle it. Expected 1. Okay. Next one is 7. 1, 7, 3, 2. Okay, 3. 2. One, all 1, the last one's 3. One. 1. 1. Last one is 3. Okay. Oh, we passed quite a few. Okay. So of course this is the first thing we need to analyze. The last one's also not right. Okay, so what happened here? Shall be 7. Right, we're gonna get 7. Let's take a look. Yeah, this is not right. This is already wrong. The second one, I put 1, 0 in. Oh, no, wait. Hold on. That's 1, 0. 2, 1, 0. 3, 1, 0. Okay, so now I can go 1 and I can go 0, right? Then, we go j minus 1. Wait, hold on. we go to j minus 1. I want to find where we can make it, right? So if this we can make it, right? We shall make it, right? We shall make it. And then we say go previous, right? Yeah, I didn't consider the 2. You know what? I do think it's necessary to handle this. So I think this is correct. This is okay, right? And then, because I want to take this, then what we shall do, hold up. If k is equal to 1, okay? If k is equal to 1, then I can just take the previous one, right? Then we say dp minus 1, 1 shall equal to maximum dp minus 1, 1, right? And then 1 plus dp. If I take this, I need to find a maximum ending at this. So it's I minus 1, 1. Right, I minus 1, 1. Right, if k is equal to 1. Lift this, right? And then we say if k is equal to 2, then k is equal to 2. No, k is smaller or equal to 2. Then do this again, but then be maximum defeat this 1 plus I minus 2, right? But has to be I minus 2 if I minus 2 is larger equal to 0, else it's going to be 0. So with these I handle, and then I handle the remaining. Now we pass this one. Okay, they all pass. Check the remainder. They all pass. Okay, so that was good. Let's run some other things. 2000 from random import rand int import string. Okay, then we say for this in range 1 to 100 test cases, test equals join. For this in range, let's do 100 in length. 100 in length. Yeah. When it says rand int. Alright. I was going to use string, but char. I think it's 97 plus rand int 0 to 26. Test k shall equal to rand int 1 to Let's do 1 to 100. Let's 1 to 150. That's the 1 to 100. Okay, on print. Test. What? Oh. Shoot. That's not right. 96? I forgot. Oh, should be 25. Yeah, I had too much. Should be 25. Okay. This one should be right. Okay, it could be like, it might be all zeros. Yeah, lots of zeros. That's not fun. So instead of this, we'll do 10. You know what? Better, yeah, do 5. Oh, we shall have more likelihood of hitting. Okay. Let's try this. We got it. We freaking got it. Oh my word. Oh my word. Oh my word. Wow. That's not the best performance, but man, did we get it. Is that considered O(n) squared? I won't say it's O(n) squared. It's more, it's O(n) something, right? Because we have 2 for loops, but this for loop is dependent on, yeah, worst case scenario, it is O(n) squared. I agree. Yeah, it's O(n) squared. This is O(n) squared. Ooh, man, oh man. Ah, this idea works. Damn. All right. I'm very happy, surprised and happy at the same time. And it works. I'm surprised and happy. All right, so now we're gonna, well, we have the DP idea, right? So the DP idea is specified in the definition of DP below. All right. At each SI, right, we need to find all possible palindromes ending at SI. Each such palindrome represents a partition. Then we just need to find the max number of substrings. Number of palindrome substrings that fit, that correspond, right, to each partition. Now the edge cases are when the palindrome is when k equals 1, where in a single letter can be a legit palindrome, and when k is smaller or equal to 2, where where a substring like AA can be a legit palindrome. For all the other cases, we need to check, right? We need to check all the palindrome scenarios of Si-1, because the only way to form a new palindrome ending at Si is to have the letter right before the palindrome ending at Si-1 equal to Si. For each palindrome ending at Si, we need to check, right, the max number of substrings, right, not just substrings, right before the current palindrome ending at Si. Here is a very important trick. We keep the max number if at Si, right, if at Si we have number of substrings smaller than at Si-1, we keep the larger in the DP. This allows us to refer, right, this is important and can be illustrated as such. Say at Si-1, it can form a palindrome with Sj, right? So now we need to compare Sj-1 and Si. If they are the same, then we have a new palindrome from Sj-1 to Si. Alright. Then we need to know the max number of substrings, legit substrings from S0 to Sj-2. Now, it is likely that the max is reached, right, somewhere between S0 and Sj minus 2. If we only keep in the DP the exact number of substrings, right, legit substrings at each letter, we will have to run another loop searching from j minus 2 to 0 to find the max. However, we can also keep track the max, right, at each letter. Then we only need to check dp j minus 2 to find the max substring from S0 to Sj minus 2. That's the trick. And then runtime is O(n) squared, and oh, this is our time. Oh, that's a good one. There's a greedy. There is a greedy. Oh, they do two. Yeah, I see. Yeah, I'll stick to mine so I understand. We have strings. Caitlin, that's palindrome. Create DP array. True if it's palindrome. Else false. Okay. Then we solve. Ooh, hold on. Length. Ending at J. Wait, hold on. I, J will be length. But anyway, this is defined if I to J is a palindrome. How do we solve this? Position and S. This is memorization. So what's this? This is from this to the end. How many, right? So from this to the end, how many? I say, if I take, don't take, solve position 1, which means take equals maximum 1 plus, oh, I don't take. So for each position, I can either take it or I don't take it. If I don't take it, it's this. If I take it, then, oh, shoot. Damn, this is easy. Oh man, I see what it means. Wow. Wow, what can I say? This is the solution from man, is this solution has deconstructed the problem so much that it makes it look almost too easy. All right, 2 steps. First, we create a DP table that records whether where dp ij records whether si to j is a palindrome. Then we run a top-down DP to find the max substring from si to the end at each step. We can either not take si or take si, right? When we take si, we need to find all the palindromes starting from si and with length larger or equal to k, and find all of their count of substring. Yeah, that's O1 squared as well. Okay, let's code it ourselves. All right, so first we need to find palindrome. How do we count palindrome? So we have I to j, right? To find I to j as a palindrome, we need to know if the inside is a palindrome, right? And that's a bigger I and a smaller j. Holy crap, how do we do this? So if we start from this, right, we know this, and then we do this. So if we want to find if is this a palindrome, then we need to know if it's inside is a palindrome. Right, which means if we have like I 0, 1, 2, 3, j 0, 1, 2, 3, I know all of these are palindrome, right? This is true, 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 true. Now we'll find a 0, 1. To find a 0, 1, we just need to know if they are the same, right? We want to find a 0, 2, right? We need to know 1, 1. 0, 3, right? We need to find a 0 to 3, so we need to know 1, 2. But 1, 2 we haven't computed yet. So what's the order? I mean, we can do this. Let's say we can do this, and 1, 2, you know this, right? And then length is 3, right? And then we need to do, oh, we're going diagonal. Because 1, 3 we need 1, 3 we need a 2, 2. Well, we have 2, 2. So this is 3. That's why it uses the length. So 4 we need to have 3. So 0, 3. Yeah, let's say this is done. And 0, 2. 0 to 2 we need 1, 1. So we have to get this done, we get this done. And then we need 1, 2. We have it. Oh, okay. Anyway, n equals line s. Okay. dp equals false times n for is in range. Okay, so for L in range 1 to n, that's the length. For I in range, alright, 0 to this, j shall equal to I plus L minus 1. Alright, now if I is equal to j, dpij true, right? Otherwise then L if I plus 1 equal to j. Right? Then dpij shall equal to si equal to sj. Else then dpij shall equal to si equal to sj and and something, and dp something. What is dp something? I plus 1, j minus 1. Alright, so this is I plus 1 equal to j. Okay, so that's that. Then def solve index turn a int, right? And from func tools, where are you, cache? Okay. Now we say, yeah, if index is larger or equal to n, turn 0. Otherwise, res shall equal to solve index plus 1. Right? This is not take s index. Or if we take s index, then we should say for I in range, we can actually go index plus k, right? Minus 1 all the way to n. So for everything, we should say if dp from index to I, I want to call it j. Okay. If this is true, then res equals maximum res solve. Because that's to j, so it's j plus 1. Alright, we're going to find a maximum. Yeah, so we'll check this. And take this. Right, now we need to find the maximum from this to the end. Right? If everything to the end. And eventually, actually it's 1 plus, because I myself 1 plus this. And eventually we're going to return res. Right? And then we just return solve 0. Oh, so good. Oh, okay, I have to check here. That is not right. What the hell? Index out of range. Huh. Yeah, because I go to the last one, right? If this is equal to j. We need to j equals this. If j is j is smaller than n. Yeah. Look at that. Look at that. So much simpler. It might not be as fast, but yo, don't time out. It might not be as fast, but Lord, is this one good. I mean, good in terms of just the simplicity, right? The simplicity. I really appreciate the simplicity. Yeah, this might not be fast, but it is really simple. The idea is really simple. Yeah, like we can actually, for each role we can get what, because we go every single one. We don't have to go every single one if we use another DP, right, to record what index that has the palindrome, where like this is true, so we don't have to go through every single one. So we can basically the same as this, right? We know where to go for the next one. But it's good. It's good. I mean, they have another solution. Oh wow. Oh yeah. They say it's okay. It's not Owen squared. I mean, we take Owen squared for this. different solution. Why only take these two? Yeah. Is this as greedy in it? If one palindrome is a substring of another palindrome, then consider the second one when not. When palindrome is, if one palindrome is a substring of another palindrome, then consider the second one will not increase the total number of non-overlaps. Thus, consider minimally allowed palindrome of even and odd length. Ah. So we have a palindrome, right? And we have all the other palindrome. If we have a palindrome, then we have a lot of palindromes smaller, right? Then for the smallest palindrome, and because these are palindromes, so they themselves do not form. So the thing is, we always want to use the smallest palindrome. I mean, it makes sense. If you use the smallest palindrome, it'll increase the chance of forming another palindrome. Right, so don't use a big palindrome every time. You always use the smallest palindrome you can find, which is just. But it still doesn't explain why we just search for k and k plus 1. Because it has to be k. It has to be k plus 1, right? What we're saying is if we have a k or k plus 1, and if we have a bigger one, then we don't have to check the bigger one, because the bigger one will definitely not perform as well as the smaller one. Because if that is a palindrome, then it will be covered. If otherwise, well, Solution 3. Solution 3. This is the greedy version. Same setup as solution 2, but we don't have to go through each index in the solve function. We only need to check the smallest possible palindrome, because if we have a larger palindrome, it is a palindrome longer than k. It is always better to just consider the smaller palindrome of length k, because yeah, if we consider palindrome length k, yeah, it's because consider palindromes of longer lengths does not increase the chance of finding new palindromes. This is the greedy part. So we'll leave this as is, right? And then this is fine. This is not take, right? And then if dp index, I want to take index plus k, which is the length k, right? Res equals maximum, res 1 plus solve index plus k, right? This is length k. If dp index plus k, length k plus 1. We need both to handle even or odd, even and odd palindromes. Okay, so if this now say res equals maximum res 1 plus solve index plus k plus 1. And then we return this. Solution 3. What? Still out of range? No, index plus k. I have some issues. I think it should be right, and then this should be if index plus k minus 1 is smaller than n, so index plus k smaller than n. There we go. Oh, this is even better. Huh. How? Yeah? How come this one fail? but this one works. It doesn't make any sense. Hey, seriously, this doesn't make any sense. Are you serious? This one's faster? I don't think so. Oh, I why? And this one will be wrong. This one takes a long time, I guess. It doesn't work. It doesn't work. So this, and this is O(n) squared, and it times out. What the heck? Can say is dp of is pal Yeah, I can't believe this computer directly is faster. Not only faster, but much faster. String manipulation. And what the hell is this? Oh, shoot. I didn't see that. Huh? What? Oh, shoot. Didn't see that. My bad. Oh. Well, it's not a nightmare, but yeah, could have been better. Alright, that'll be it. I'll see you guys.